Welcome to the third part. Now we are discussing the Bohr's model of atom. Bohr retained the basic postulates of Rutherford model of atom but proposed three new postulates which removed some of the problems associated with the Rutherford's model of atom. The first condition is the angular momentum quantization condition, which said that an electron can revolve around the nucleus in only those circular orbits for which angular momentum of electron is an integral multiple of h over 2 pi. That is, L is equal to mvr equal to nh over 2 pi with n as an integer having value 1, 2, 3, so on. Second, he gave the concept of the stationary orbits, which said that when electron is revolving in any given orbit for which angular momentum condition is satisfied, then this revolving electron, it does not lose its energy. So energy of an electron revolving in this quantized orbit around the nucleus is a fixed value. It doesn't loses any energy. So if its energy is not lost, its velocity will be, its speed will be constant, due to which it will keep on revolving in its particular orbit. This type of orbit in which electron does not radiate out or lose any energy, we call this as the non-radiating orbit, or we also call it as stationary orbit. Stationary means it is not losing any energy, its energy is constant. In order to remove problem associated with the spectrum, he proposed the frequency quantization condition, which says that an atom can emit a radiation or absorb a radiation in the form of discrete energy photons only when electrons are jumping from higher to lower level, or they are moving from lower to higher orbit after absorbing the energy. This means that if electrons orbits are quantized, then the radiations they will be emitting when the electrons will be jumping from higher to lower orbit, or the radiations which will be absorbed when they will be moving from lower to higher orbit, that means their emission spectrum or absorption spectrum, they will also contain radiations which will have discrete frequencies. This means that if E1 and E2 are the energy of these orbits, then the frequency emitted or absorbed by radiation, it will be h nu equal to E2 minus E1 and frequency will be E2 minus E1 divided by h, Planck's constant. This is the Bohr's frequency quantization condition. So now let us discuss the mathematical details of Bohr's theory of hydrogen atom. So here we have the circular orbit with the nucleus with the charge Ze present at the center, and the electron are revolving in the anti-clockwise direction with the tangential velocity v, and the radius of the circular orbit is r. So centripetal force required for the revolution is coming from electrostatic force of attraction. This means that mv square over r is equal to k into Ze square over r square. From here we get mv square equal to k into Ze square over r, we take it as equation 1, or r is equal to k into Ze square over mv square. This is second equation. If we apply angular momentum quantization condition, that is L equal to mvr equal to nh over 2 pi, from here if we get the value of r, it is equal to nh over 2 pi mv. If we use equation number 2 and equation 3, so by 2 and 3 we will have k into Ze square over mv square equal to nh over 2 pi mv, or if we solve this equation for the velocity, v will be equal to 2 pi kz e square over n into h. Here this equation give us the velocity of electron in any nth orbit, so we put n as a subscript with the velocity. Here 2 pi k z e and h all are constants. This means that velocity of electron in any nth orbit is inversely proportional to the order of orbit. So as the order of orbit is increasing, first, second, third, fourth, so on, velocity is decreasing. Reason, as electron is moving, revolving into higher and higher orbit away from the nucleus, attractive force between nucleus and electron is decreasing, so centripetal force required is also decreasing, so speed is also decreasing. So if we use this equation 4 in the third equation, so if we use 4 in the third equation, the value of r will be equal to nh over 2 pi m into nh over 2 pi k z e square. So this will give us the radius of the orbit, r equal to n square h square divided by 4 pi square m k z e square. This is the radius of any nth orbit, so we put subscript n. From this equation again, Rn, radius of any nth orbit, is directly proportional to square of the value of n. This means that as the value of n is changing as 1, 2, 3, 4, so on, the corresponding radii are increasing in the ratio of 1, ratio 4, ratio 9, ratio 16, and so on. Here n we call as the principal quantum number. Let us find the radius of the innermost orbit, that is what we call as the first Bohr orbit. When n is equal to 1, we call it as the first Bohr orbit, for which radius is indicated by a naught. So this value of a naught, it is equal to h square over 4 pi square mk into e square. All these three factors are constant. If we solve by substituting all the values of the constant figures over here, we will get the value 5.29 into 10 raised to power minus 11 meter, or we can write it as 0.53 angstrom. This means that the first orbit, it have a radius of 0.53 angstrom. If we find the speed of the electron, we know that Vn is equal to 2 pi k z e square over nh. Now here, if we put z is equal to 1, Vn it will be equal to 2 pi k e square over h. If we multiply this thing with the speed of light and also divide it with, we will have 2 pi k e square over ch into c by n. We can write this equation as Vn is equal to alpha into c by n, where alpha is 2 pi k e square over ch. We call this as fine structure constant. and its value is equal to, after substituting the values of constant quantities and solving, the value of alpha comes out to be equal to 1 over 137. So if we use over here into this equation, we get V equal to 1 over 137 into C by N, and for N equal to 1, V1 is equal to C over 137. That is, the value of fine structure constant indicates that the speed of electron in the first orbit of the hydrogen atom is 137 times lesser as compared to the speed of the light. Let us now find the energy of the electron. An electron around the nucleus possesses kinetic energy due to its circular motion around the nucleus, and also electrostatic potential energy due to the attraction between the nucleus and the electron. Kinetic energy is given by half mv square, which is equal to k into z e square over 2r. Here we have used first equation, and potential energy is given by k into q1 q2 over r, which is equal to minus k into z e square over r. q1 is equal to ze, charge of the nucleus, q2 is equal to minus e, charge on the electron. So total energy is sum of kinetic and potential energy, which is equal to kze square over 2r minus kze square over r, which is equal to negative kze square over 2r. So from here we get idea that the total energy is same as that of the kinetic energy, but with the negative sign. Now in this equation, if we substitute the value of the radius of nth orbit, then the total energy of electron in the nth orbit, it will be equal to minus k z e square over 2 into 4 pi square m k z e square for nth orbit. Energy is minus k z e square over 2 into 4 pi square m k z e square over n square h square, which give us the final value of the energy in any nth orbit as minus 2 pi square m k square z square e raised to power 4 divided by n square h square. This is the expression for the energy of an electron in any nth orbit. Total energy is negative in nature, which indicates that this is the energy of the bound state. Bound state means it is the energy of an attractive system in which electron is attracted by the nucleus. In this equation, we get that energy of an electron in any nth orbit is inversely proportional to the square of the value of the order of the orbit, that is the principal quantum number. So as the value of n is increasing, the energy of the electron is increasing. So electron, if we put n equal to 1, electron in the first orbit, it possesses maximum negative energy. Maximum negative energy means minimum energy. So as the value of n will be increasing, the value of the energy, it will be increasing towards its maximum value, that will be equal to 0. That is when the distance between the electron and the nucleus is equal to infinity, where the attractive force between them disappear. So potential energy will be also 0, kinetic energy will also be equal to 0. Now let us discuss the spectral series of the hydrogen atom. We know that for any nth orbit, the energy of electron is given by minus 2 pi square m k square z square e raised to power 4 over h square into 1 by n square. Now, if we use Bohr's frequency condition, whenever an electron is making transition from higher to lower level, it is going to emit a radiation whose energy will be equal to the difference of the energy between the two corresponding levels within which the transition is made. So if an electron is making transition from a higher orbit n2 to a lower orbit n1, then the difference in the energy of these two levels will appear in the form of the photon, which will have the energy h nu equal to energy of the higher orbit minus energy of the lower orbit. So if we use this energy of the equation for energy in any nth orbit and we do a little simplification, we will have the value 2 pi square m k square e raised to power 4 over h square into 1 over n1 square minus 1 over n2 square equal to h nu, or nu will be equal to 2 pi square m k square e raised to power 4 over h square h cube into 1 over n1 square minus 1 over n2 square. This gives us the frequency of the radiation emitted. And in all these calculations, the Z is equal to 1 because we are doing it for the hydrogen atom. Also, because C is equal to nu lambda, C is equal to nu lambda, we can write the above equation as C by lambda equal to 2 pi square m k square e raised to power 4 over h cube into 1 over n1 square minus 1 over n2 square, or 1 by lambda reciprocal of the wavelength, which we write as nu bar. Nu bar is wave number, which will be equal to 2 pi square m k square e raised to power 4 over c h cube into 1 over n1 square minus 1 over n2 square. And this whole equation we can also write as nu bar equal to r into 1 over n1 square minus 1 over n2 square, where r is the Rydberg constant, which is equal to 2 pi square m k square e raised to power 4 over ch cube. If we substitute the values of all the constants, we will get the value 1.0973 into 10 raised to power 7 per meter. So this gives us the Rydberg formula, with the help of which we can find out the spectral series of the hydrogen atom whenever it will make any certain specific transitions from higher to the lower orbit. Now the different spectral series of the hydrogen atom, they are combined into various groups. The first name of the spectral series is known as the Lyman series. If an electron is making jump from any higher level, that is from second, third, fourth, fifth or so on a higher level to lower orbit, that is n equal to 1, then we get the first spectral series, which is called as the Lyman series, which lies in the ultraviolet region, for which the wave number or the wavelength is equal to 1 by lambda equal to r, which is equal to 1 over 1 square minus 1 over n2 square, with the value of n2 equal to 2, 3, 4, 5, so on. If electron is making transition from third, fourth, fifth, sixth, so on to second orbit, we get the second line called Balmer series, for which wave number and the wavelength is equal to 1 by lambda equal to r, 1 over 2 square minus 1 over n2 square, with n2 value starting from 3, 4, 5, so on. It lies in the visible region. If transition is made from fourth, fifth, sixth, so on level to third level, then we get Paschen series, which is in the infrared region, for which Rydberg formula is 1 by lambda equal to R into 1 over 3 square minus 1 over n2 square, and the value of n2 starts from 4, 5, 6, 7, so on. For bracket series, the transition is done from 5th, 6th, 7th, so on level to the 4th level, for which formula is 1 by lambda equal to R into 1 over 4 square minus 1 over n2 square. Here n2 starts from 5, 6, 7, so on. It is also lying in the infrared region. Last we get P fund series. P fund series is obtained when the transition is made from 6, 7, 8, so on level to the lower orbit, which is the 5th level. So in this case, wavelength is equal to 1 by lambda equal to R 1 over 5 square minus 1 over n2 square, with the value of n2 ranging from 6, 7, 8, so on. It is also lying in the infrared region. So these are the different spectral series which are obtained in the spectrum of the hydrogen gas whenever a transition is made by the electron from any higher orbit to the lower orbit. We can represent all these spectral series on the spectral diagram like this, which shows the various series. For example, Lyman series, which shows the transition to the first orbit, Balmer series, which shows the transition to the second level, third Paschen series, which shows the transition to the third level, and similarly bracket and P fund, which shows the transition from any higher level to the fourth and the fifth level. So in this way, various spectral series can be obtained. Thank you.